Hey everybody! Hey everybody! We made it. We came to the final tutorial of the class. So today we're going to talk about the numerical solution to the equation we developed so far. So we're going to collaborate with our old friend, the computer. And the class is going to be divided by two. It's going to be a very short class. The first part is going to be about the theory behind the simulation, the numerical code. And the second part is going to be talking about the final project, answer your questions, and give you some guidance. Okay? So without further ado, let's dive into the numerical simulation. So when we recall what we did, so I'm going to do it like this. We have the lungs, and we're dealing with a single airway, and then we can interpret what's going to happen to each of the airway. So just give me a reminder. I'm going to go to the main board here, and I want us to do a kind of a recap for all the class, what we have done so far. So we have the lung, very complex structure, and we have a single airway. And inside the airway, we have a particle. So why would this particle, our drug, want to deposit on the tissue? What's mechanisms? First, gravity. You have the force of gravity, that's great. And what else affected? If we have electrostatic attraction, if this is a positive, it's induced charge on the tissue, so we may have also electrostatic force. Great. And what want to stop this? Huh? Yeah, let's make it bigger. Okay. So this is the airway. So we were in gen 15, and now we're going to increase to gen number 3. Okay. So this is the particle. We said gravity, mg. We said electrostatic force may want to encourage the particle to come to the tissue, which means this is charge, and it's going to induce some charge over here. What want to hinder these forces from motion? What want to stop them? Drag, right? Drag. So maybe we have here some drag force, and don't forget that we have some flow that's feeding the lungs, so we also have some velocity profile, so we also have a drag force in this direction, right? Because of this motion. So our problem, if the flow is in that direction, so the drag is in that direction, let's remind us. So if I'm going to split this into the x-axis, we have the drag force at the x-coordinate, which equal to m du to dt. And what is the drag force? Now I answer your question. It's the velocity of the fluid minus the velocity of the particle, right? Divided by, if we assume Stokes drag, we have here the mechanical mobility, which actually take care of which fluid it is, what is the size of the particle, what is the shape of the particles, all this stuff inside B. Here we have m du dt. And you know, to solve this, this is of the particle, to solve this, this is a joke. Why this is a joke? Because this is a ODE, right? We see ODE, and this is linear, right? This is linear, non-homogeneous, right, because of that. And we have the solution. The solution would be that the velocity of the particle at the x direction would be the velocity of the flow with some modification because of, you know, the flow, the difference that we have here. So this is the homogeneous solution. This is the private solution. And if you're going to take times that are much larger than this tau, actually they don't have to be that large. If you recall that 3 tau or 5 tau is already killing the exponent, right? What is this tau? This is the relaxation time. How much time it takes to the particle say, oh, there's a flow and you want to take me in that direction. So this is a very fast. This is 10 to the minus 6 approximately in aerosol delivery to the lungs, right? So if you're going to choose, I don't know, 3 microseconds or even 1 millisecond, right? 1 millisecond, you be much far away from that, and you can neglect that and say that the particle behave very, very similar to the flow, and this is one of the main problems in the lungs. You cannot take particle outside of the flow. They want to follow the flow. Okay? Okay, great. What's happened in the y direction? So what do we have? First, as you said, we have gravity. I put here the axis, right? X and y. We have gravity. What else do we have? We have the drag, right? That want to resist it. So I'm gonna note v of the particle and not u, divided by b. And I assume there's no flow in this direction. It's uniaxial, all the flow in that direction, minus the electrostatic force, right? 4y squared. And note that here you have the 4 because we assume image charge phenomena. Okay? So 4y squared minus, you want to bring the particle into the tissue, and this is equal to may, right? And now I want to solve this equation. I see that this equation is an ODE, right? I see this because a, y, and v, and y, you know v is the derivative of y, a is the double derivative of y, right? So we want to solve, this is an ODE, but we are screwed. Why we are screwed? What we see here is this equation is linear. So if I want to find the real solution, which is a superposition of private solution and homogeneous solution, that's going to be a joke. It's not going to be right. So how are we going to deal with this monster? And the answer for that is numeric. Okay? And to do the numeric, we need first to address these two. Okay? But we're going to try to solve it, and maybe in your drug delivery situation, you're going to have some term which is going to be very initiative and smart and sophisticated, and they're going to fuck everything up. Okay? So how are we going to deal with that? I go to the board. So the first thing I want to deal with is to remind us what is the velocity, because we need to go to the really basic to solve the numeric equation. So what is the definition of velocity? Remind me, guys. Velocity equal to what? Again? Great. Displacement. This is v, so we are dealing with y, right? But you're correct, it's a distance. So it's what happened. Where are you right now? Minus where were you dt ago, right? And divided by dt, yes? Divided by dt, and let's not forget the dt is what? Is really big or really small? Very, very small. So what I want to do is to present this idea inside my equation. Can we do that? So the idea of that, so how can we deal with that? So just a reminder, what would be a good dt for the lungs? How much time it takes to breathe air in and out? Approximately 4 seconds. Okay? So if I'm going to choose 1 millisecond, it's thousands of times smaller than that, right? But we're dealing with one single airway. So we have 23 airways, so approximately 2 seconds in each, a tenth of a second in each airway. We're still hundreds of times smaller than that. And what's really cool about that it's killing our exponent, right? Because the dt that we chose is much smaller than tau, right? We're going to come back to that later on, but just to have the notion, this idea. Good. And by the way, when you do numerical simulation, nobody promising you this is going to work. You need to do some checking, validation, to make sure this is valid, this is okay. The simulation is okay. Okay? So we have v equal to y, t, and I'm just going to write y. This is what we're trying to find. Y, the height of the particle at any time, minus, and now I want to show you something. I can present time as a vector. T vec at time I is just I multiplied by dt. How much dt have I counted? Okay? I'm at the first dt, I'm I'm at the first dt, I'm in the second dt, third dt, until the simulation is over. So I can count time with dt's. So if this y, let's call it yi, the current I, this is one step before. You see what I mean? Yes? Divided by dt. Okay? So if I gonna reorganize this, you already tell us that if you know v one step before, right? And you have your y, dt, plus yi minus y, you can tell the location of the particle. So what you actually need is an initial condition. So if this is given, what is the initial height of the particle?
Why is it Vy to the minus 1?
This?
No, the V is Vi times I minus 1.
I minus 1 multiplied by dt, I minus 1.
Why? Yeah.
Okay, Vi. If you know the current velocity, the dt, the y, you can find the height of the particle. So that's the idea of velocity. But we're dealing with much complicated question. What are we dealing with? We are dealing with acceleration term also. You see it here? So what is the acceleration term? So in a similar way, let's go to this side of the board. So in a similar way, we can say that ay is equal to the limit of dt go to 0. Now acceleration is the change in velocity, right? So this is v at time t minus the previous t, the t that we had before divided by dt. And of course I can write this in a much simpler way. I can write what is the velocity. The definition of velocity is dt, y minus yi minus 1. When I don't write anything, I mean yi. Okay? So I don't want to write a lot. Okay? This one, here what we have, it's the previous step. You see, it's the previous velocity, the old one. So this is yi minus 1 minus y minus 2. You see that? If I'm gonna reorganize it, I'm gonna see that a of y is dt squared, because you have this one and this one, you see it. Here you're gonna have the y that we are trying to find. This is what we're actually looking for. We want to find, I remind you, what is the solution of this ODE, which means what is y as a function of t? What is the height of the particle at any given moment? Going back to here, we have y minus 2yi minus 1 plus yi minus 2. You see it? So we found the acceleration term. We found the velocity term, going there. So we found the velocity term. And all I need to do is to plug everything inside here and hope the equation will not become so messy. So I want to plug everything here. So let me draw it. So I'm going to clean the board. We understand that, right? And what we're going to do, we're going to try to get rid of the ODE idea by just putting what are the value of v and a explicitly. So we're going to write it again on the top. We are looking to find what is y, and we have minus mg minus v divided by b minus k q squared divided by 4y squared equal m-a-y. And right now, we want to plug in the ugly acceleration term and the ugly velocity term. Let's do it. So, mg stay unaffected, minus mg, minus 1 over b, and the velocity, which is yi minus yi minus 1 divided by dt. So, I want just to give us a focus, what we are trying to do at the moment, okay? So we're trying to solve this equation, but we would not try to solve it for any moment. We're going to try to solve it. This is the equation, and this is the particle trajectory, just what's happened in a single dt. That's the idea. what's going to happen to the particle? Given that I know its initial height, ui minus 1, this is h0, and also know its velocity, v, at this point, which is a function of ui minus 2 and ui minus 1, which means I have this, this, and this. They are the same. Yeah? I have this and this. Initial condition. So that's what I have. So this is known, this is a constant. This is known, this is a constant. Minus k q squared for y squared. Okay, that's what I want to find. Remember? I want to find y as a function of time. Perfect. This is yi, yeah. This is yi. You can put her index I, but I just said that that's what we're going to write the most, so I don't want to confuse us with the rest, so I'm just going to omit it, but you are correct. M multiplied by the acceleration term, which has the y that we want. This is a good one. That's right. Here y squared, don't forget it. Y minus 2y previous step plus y2 step before. Right? This is the squared. Okay, this is the equation we want to solve. And I don't know what's about you, I hate fractions. So let's multiply everything by dt squared by 4y squared, and by b. Okay? Good? If I'm going to do that, I'm going to get minus mg 4b y squared, don't forget it, t squared. Remember, this is a constant. We define it. It's a millisecond, right? Minus y, hey, I want to find u, minus I minus 1 multiplied by 4y squared. Oh, this is very important. I want to find u, dt minus k q squared b dt squared. Remember, this is a constant, right? We know k, we know q, we know the mechanical mobility, we know dt squared, equal to the mass y, I want to find u, 2y I minus 1 plus y I minus 2 4b y squared. Okay, so this is the equation, and I want you to see something very, very interesting. Everything here are constants beside y. You see it? Right? We have here y, here y, here y, here y, and here y. Exactly. It's a polynomial. Let's organize it in a better way. We can write it as follows. So I'm going to clean this board and write it. So we expose the secret behind this numerical solution. So we had a very messy equation, but this equation ended up to be something not that frightening. It's ended to be C3. This is not working. Here it is. So this polynomial end up to be C3 multiply. You know what? I'm going to do it on that side of the board because I want to be close to the TV. Okay? Let's clean the board. So we have C3 multiply by u to the third. And if you're going to look at the equation and reorganize it, you're going to see that the coefficient of C3 is C3 equal to 4 tau plus 4 dt, right? Tau, reminder, I'm coming here. You see m, camera with me. You see this and this. Tau, if you recall, tau is equal to the connection between them. It's m multiplied by b. Remember, the relaxation time is related to the how hard is to move to accelerate my particle, the mass, right? And how much it reacts to the drag. This is building the relaxation time. So to write less, I put tau, okay? Good. So 4 tau, 4 dt, and this is what? Is a constant, right? This is approximately millisecond, right? This is microsecond, so it's actually equal to that if you want to do it in an engineer way, but let's leave it as that way. Plus, we have C2 multiplied by y to the power of 2, and C2 is, this is the most scariest coefficient, 4 tau yi minus 2 minus 2y I minus 1 minus 4 dt yi minus 1 plus 4 tau g dt. So as you see, this is the coefficient that have all the initial conditions. What it was before, what was before, what was before, what was much before. Right? But it's a constant for the given time. Good. We have here C1 multiplied by y to the power of 1, right? And C1, if you're going to look at the equation, is equal to 0. There's no term of y in our problem, right? Okay. And we have coefficient of the power 0, right? Which is equal to the electrostatic term, d dt, right? It's a constant. And just a reminder, why we are so in love with polynomials. Do you remember? There's 3 reasons why we very, very love polynomials. The first one, they're very easy to derive, right? They are very easy to integrate. But last but not least, it's very easy to find their roots, right? So I don't know if you know this guy, this Italian mathematician, but he is one of the people that invented the imaginary numbers. So he didn't believe or understand imaginary number, but he just used them as a tool to find roots for the cubic equation. And this is the cubic equation. So you don't need to work hard. You know, as you know that you can do one. You recall the parabolic equation. You have y equal to 2 times C2 minus C1 plus minus C1 squared minus 4 C1 C0. Remember this equation? When you have 2 solutions? So we have the same thing for the cubical. But the math is very, very unpleasant and ugly. But don't worry, we are collaborating with our old friend, the computer. And in MATLAB, you have a command that finds the roots automatically. So you just need to do the roots. This is the command, and you're going to need it to the final project. Roots of this coefficient, it's the other way around with the parentheses in MATLAB. So C3, C2, C1, C0, voila. And it's going to give you in the other side the vector of the solutions. How many solutions do we have to this equation? 3. So we still fucked up, right? Because we need to choose which y is the relevant. But we're kind of lucky because 2 of the solutions going to be complex. No way y it's going to be complex, right? What is the boundary condition of y? The lowest value we can get is 0. The highest value we can get is the diameter. So it must live in this realm, right? So guys, we kind of did it. So right now, go here. So what actually we have, if we're going to give a particle, let's say over here, an initial height, initial velocity, let's say, I can calculate what it's going to do after dt, right? If I know what it did after dt, I have the new velocity and the new location of the particle. And I can repeat that again, and again, and again, and again, and again. So each dt like that, I'm solving this cubical equation using this function. Just find the roots and take the real number. So don't worry, I'm going to send you the MATLAB code that I have, but that's what I want you to see. I define the coefficients, 4 tau multiplied by 4 dt. C2, I define it later, define it as a vector, you're going to see C1 is 0, C node is B multiplied electrostatic terms, and then I have a command to find the roots of the equation. And I said, if the imaginary number is equal to 0, if you don't have imaginary number, take this result, add some spice, some diffusion to the solution, because we neglected the diffusion term in the force balance equation, right? And that's it. You have the new location of y. Any question?
Why did you definitely have to imaginary?
You need to see the math. The general solution would consist imaginary numbers. And you can actually see the matrix. In my simulation, I have a matrix of the solution, and you see that two sides of the matrix are, two rows of the matrix are always imaginary. So we are lucky, but this is a good point. Nobody promises you're going to be that. Our situation, it's solvable, finding the roots. If in case we did have a complex number as a solution, we need to do another step of understanding what does it mean, the complex number. Is that clear so far? What? If the imaginary number is 0, it means that I have only complement of real number. I don't have imaginary. So this is the solution of y, because y must be a real number. So guys, I'm very, very excited. I promise you it's going to be short, but we finish. That's what I want to share with you in this class. So just zoom out. Some of you have been with me from Physics 1, continue to Physics 2, continue to Fluid Mechanics, and I didn't expect to have another class with you, but we had it here, the drag delivery and reciprocatory flow. Thank you so much for the opportunity to teach you. I think we learned a lot in this class, and after that, let's talk about the project, okay? But thank you very, very much.
Question before.
Go ahead.
I want a clarification about the eye.
The eye.
So you say that
with the camera, what? Yeah. If we have a question about the eye, the index, yeah.
That we want to find the trajectory in a small part that called dt. So in MATLAB we must define the eye by for loop. That's right.
By what?
A for loop.
For
loop.
Okay. So you have I, right?
So I'm wondering what is the beginning and the end for
So think about it, that you want the first time to be times 0, right? So you want your I to be 0, right? And the tvec, it's going to be I multiplied by dt. And if this I increase in time, it's first is 0, then it's 1, then it's 2, then it's 3, then it's 4. You can have a vector of time, you see it? Which depends on how many times you have dt in your, how much counts of dt that you have. Okay? Cool? Perfect. Okay, so this is the crucial moment. So we go, another question? Why do you have 4 here? The reason that you have 4 here is when we did the electrostatic force, we saw that we have this distance y, right? And we said that we can use the image charge solution. Instead of this induced charge, we can replace it by that. And here you have another y. So the Coulomb force between them is 2y, right? kq squared. And the distance need to be squared. So you end up with 4y squared. Yes? Clear? So another question about that? Okay, so what we're going to do, I'm going to go outside to call Josue. We're going to make a new video. And I'm going to tell you about the final project. Okay? All the small details that you want to hear. Okay? So stop the video. Perfect.